go ahead and start. Right, we're all very happy to have Nick and Benjamin to talk about Lightcone Modular Bootstrap and pure gravity.
Great, thanks very much for the invitation. It's really a great pleasure to be here. It's my first time in Texas A&M, so I'm very happy to be here. So I'm going to talk about a paper that appeared a few months ago with my collaborators Virasoro, Shuheng Shao, and Yifan Wang. And here's a brief outline. So first, let me start off with just asking some big picture questions that we're not going to answer, but I just want to keep in sort of the back of our mind, just as sort of a motivation. So 2D CFTs are quite important in physics, and you might be interested in two-dimensional conformal filters for a variety of reasons. So here are three quite different reasons that you may be interested in 2D CFTs. The first is you may be interested in critical phenomena that happen in 2 dimensions. Another reason you may be interested in 2D CFTs is you may be interested in string theory and studying the string wall sheet. And a third reason you may be interested in 2D CFTs is you may be interested in quantum gravity in anti-de Sitter space. So ADS3, CFT2. And these are all three very different reasons that you may be interested in studying these objects. People have been studying these objects for a very, very long time. And yet, despite this, I would argue that we actually know, yeah.
The second and third are related, are they not?
Sure, the second and third are related, but they are.
Okay.
But of course, that is right. Yeah. Even though these CFTs have been studied for a very long time, I would argue that we know very little about the overall space of two-dimensional CFTs. So I'm going to give three questions that I don't know the answer to, and I would love to know the answer to these three questions. The first one is, as a function of the central charge C, what is the maximum scaling gap as a function of C? So what do I mean by this? You fix your central charge. And the question is, except for the vacuum primary operator, what Virasoro primary operator has the smallest total scaling dimension, h left plus h right, as a function of central charge? So I don't know the answer to this question, and in fact, even at large central charge, as central charge goes to infinity, which is the relevant limit if you're interested in quantum gravity, I don't even know if I can get an answer that scales at all with C. So all top-down constructions from string theory that we know about have some light, Virasoro primary operators order 1 above the vacuum. And maybe this is some deep fact, maybe this is just a statement about our ignorance. I don't know the answer to this. Another question is maybe a little bit more open-ended, but what universal features do irrational CFTs have? So let me make the distinction, which I'll make in this talk, between a rational CFT and an irrational CFT. A rational CFT is a 2D CFT such that under the largest chiral algebra present, so that may be just Virasoro, it may be some extended algebra, a rational CFT has only a finite number of operators, whereas an irrational CFT has an infinite number of operators. And although that's probably by far the generic case, we know much less about the irrational case. And the third question is, can we explicitly construct an irrational CFT far away from any rational CFT? So let me be a little bit more specific about what I mean by this. I would like to have an explicit example of an irrational CFT that's actually irrational. For example, it's not very, very close to any rational point. So what do I mean by this? An example of an irrational CFT that does not satisfy this criterion would be a free boson, a central charge equal to 1 free boson, free compact boson, at an irrational radius. So it is true that this operator, that this CFT has an infinite number of Virasoro primaries coming from the momentum and winding modes. However, if you just slightly perturb the radius of the free boson such that it squares any rational number, then you get to a rational CFT. So I would like an example of a CFT where it really is far away from any other rational CFT. And although it's conjectured that these are the generic case, we actually don't explicitly know of an example of one where we can prove that it really is far away from any rational CFT.
You don't have a precise definition of what far away means, really, do you?
No, my precise definition would be if I have a conformal manifold, so in other words, an exactly marginal operator, I want it to be such that even if I turn on this exactly marginal operator, there's no rational point nearby. So in other words, consider a ball, there exists some epsilon bigger than 0 such that in that ball of radius epsilon, there are no rational CFTs there. So let me be a little bit more quantitative with my third question here. And I'm going to define a quantity associated with the CFT that's related to what's going on in question 3. So let's define the twist of an operator, the twist T, to be given as 1/2 the difference between the total scaling dimension, which I call delta, and this spin, which I call J. So first, for those of you who are familiar with Bootstrap stuff, you may be used to this definition without this factor of 1/2, so if so, I apologize. This is just a different convention. And in 2 dimensions, delta is given by the sum of h and h bar, the eigenvalues over L naught and L naught bar, and J is given by their difference. So it's very easy to convince yourself that in 2 dimensions, this is simply the minimum value of h and h bar. So I'm just going to define this for any operator O. The twist of that operator is the smaller of whichever of h and h bar. And I'm going to define the twist gap of the CFT to be the smallest value of the twist amongst all non-vacuum Virasoro primary operators. So we're going to minimize TO or non-vacuum Virasoro primaries. Actually, instead of the word minimum, I should really use the word infimum, because it's possible that there's an infinite sequence of operators which accumulate to some twist. So if that's the case, then I will consider the accumulation point the twist gap. But I want to define this object for a CFT and now convince you that this is an interesting thing to look at. Why is this an interesting thing to look at? Suppose our theory has extra currents, so extra conserved currents, so Virasoro primary operators of the form h comma 0. By definition, these currents have twist 0. So if our theory has some extended symmetry, then it'll have vanishing twist gap. So I would like to consider some CFT with a finite twist gap. Now, it's very simple to convince yourself that any rational CFT with central charge bigger than 1 has to have the twist gap vanishing, because all rational CFTs have to have extra conserved currents. It's quite easy to see this. One way you can see this is that you can convince yourself that the only theories that are rational under the Virasoro algebra are the minimal laws, and these all have C less than 1. So that means that if C is bigger than 1 and you're still rational, that means you have to have a larger chiral algebra, which means you've got extra Virasoro primaries that are currents. So suppose you work really hard and you construct a CFT which has a finite twist gap. Not only do you know that that CFT is irrational, you know that it would satisfy criteria number 3, because it's far away from any rational CFT. Because if it was close to a rational CFT, that means that under conformal perturbation theory, that the current in the rational CFT would have just some small twist epsilon, and we assume that this twist gap is finite. So we're going to be looking at this quantity with an eye towards that this is sort of a measure of how irrational a CFT is. Any questions? Okay, so.
Are you aiming at description of pure gravity in 3D in all these considerations?
Well, so far what I said is quite general. It'll apply to some finite C CFT, but indeed, if you're interested in the large C limit and you also apply some surprise conditions, these may be some necessary but not sufficient conditions for some theory of gravity. But so far in this definition, I don't need large central charge to define it. You can define it for any CFT. So if T gap is strictly finite, the theory is far away from a rational CFT. So it's believed by many that if you consider a generic 2D CFT, you will have a finite non-zero twist gap. However, every CFT that we can actually compute this quantity, we get 0. So probably this is an example of a lamppost effect, where the only ones we can compute for are like very special, very free, very rational. But it's possible that there's something pretty going on, and I think it's an interesting quantity to look at.
Why do people suspect that it's not?
Well, It's related to whether or not you believe rational points are dense in conformal manifolds.
How
And
should I believe that?
well, if you don't believe that, then you will conclude that the generic one.
No, no, sorry, I meant the other one. Why should irrationals be
Well,
dense?
it's a good question. I mean, I think logically both are possible, but I think a generic CFT. I mean, I think rational CFTs are very, very special. So the intuition should be you should be kind of far away from one. If you're interacting, there's no reason that a rational CFT should be close by. But I think the real answer should be for me personally, I'm kind of agnostic about this question because we just have so few examples. All the examples we know are basically free theories where we can actually compute it exactly. So it's a little bit hard to say.
Is there anything more, because in numbers?
Yeah, that's true.
What happens there? I mean, there it's also exactly what you said.
Yeah, so I would say it's possible both ways. I think if rational theories were dense, you might think that almost all CFTs were solvable, and that you could just take the rational point, you could perturb a little bit away from this. And I think that's unlikely to be the case, but I mean, when you say it's logically possible. Any more questions? Okay, so in this talk I'm going to use a technique called the Modular Bootstrap to try to constrain T-gap. So we'll use, and I'll explain what I mean by the Modular Bootstrap for those who are not familiar. And in particular, we're going to argue that the twist gap is always less than or equal to C minus 1 over 32. We actually, I use the word argue instead of prove because we're going to give an argument. There will be some possible loopholes to the argument I'm going to provide, and when these loopholes all come up, I'll tell you what the loopholes are. But I believe that they can be sharpened to a rigorous truth, but I don't know how to do that yet. So this is the sort of the one equation summary of this talk. Assuming C bigger than 1 compact unitary CFT, which I'll define. Let me say why this is interesting before I tell you how we derive this result. I'm going to give two reasons why I think this is an interesting result. The first reason is that this is a universal statement about all 2D CFTs, including very strongly interacting, very strongly coupled CFTs that are very far from our free point. It's not very often that we get universal non-perturbative statements without any supersymmetry. So in this talk, there'll be no supersymmetry at all. This is the only Q that's going to show up in this talk. And so I think it's always worth it to consider.
When you say universal, what about inclusion of W-like algebra extension, high spin?
Very good, very good. So if there's a W algebra, then the twist gap is 0. Because if there's W algebra, there's already a Virasoro primary of twist 0. You could ask a second question, which is, under the extended kernel algebra, what's the twist gap? Which is a perfectly fine question to ask, but I'm not going to have anything to say about that question. But this is still a well-defined question to ask with a theory with W symmetry. And with W symmetry, there will still be a Virasoro primary of twist 0. So the twist gap for a theory with W algebra symmetry is 0, which indeed satisfies that 0 is less than C minus 1. Okay. So first, this is a universal statement about all 2D CFTs. And the second reason this is interesting is what some have alluded to earlier, is that for the very special class of 2D CFT, which are holographically drilled to larger radius through gravity, which again is a very special class, what I'm saying is more general than that. But for that specific class, this is an interesting number, because it turns out, I'll say more of this, but if we are equal to Einstein gravity, so in ADS3, there are black hole solutions called BTZ black holes. And it turns out that the quantum numbers of the BTZ black hole, namely its mass and its angular momentum, are related to the twist in the following sense. These black holes require that both H and H bar are greater than C over 24 plus an order 1 number. Because order 1 is in a large C expansion. So we are arguing that you always have to have a state whose twist, which is either H or H bar, is roughly C over 32. So we'd argue that you always have to have at least one state in your theory which cannot be described classically as a BTZ black hole. So in some sense, this is a no-go theorem for no pure theory of ADS3.
What is its mass compared to BTZ mass, that state?
3/4. I'll tell you more about this.
A question?
Yes.
Sorry, so where does that order one come from? Like, I thought like for massless PDC, it's just C over 24.
No, it's always in a 1 over C expansion, because when you say it's C over 24, what are you really saying? You're really doing an expansion in small g Newton, so you really can't necessarily trust the 1 or 2. You can try to compute a one loop effect and try to hope that it's still universal, but I'm just going to be sort of agnostic about the one loop effect. Okay, so this is the big picture. So any questions about where we're going or what the motivation of this talk is? Okay, now I'm going to give a brief review of the technique we're going to use called the Modular Bootstrap. A lot of what I say will be a review, and a lot of it will be based off of this very nice paper by Scott Collier, Ying Lin, and Xi Yin, and also an argument by Tom Hartman. So in this talk, I'm going to consider CFTs with C bigger than 1, and I'm going to consider unitarity, and I'm also going to consider compactness, by which I mean I want a unique SL2R invariant vacuum and a discrete stream of states. So for those of you who study CFTs, I'm going to exclude cases like Liouville theory, which does not have a vacuum. So we're going to define the partition function, the one-loop partition function, to be the trace over the Hilbert space of Q, which is e to the 2 pi I tau. Created by the left and right moving scaling conventions of the theory. And this partition function has a very, very non-trivial equation that it must satisfy, which is that it has to be invariant under large diffeomorphisms of the torus, which act via the group SL2Z. And the equation is the following. So I take any 2 by 2 matrix with determinant 1 and integer entries, and I act on my modular variable tau in the following way. The partition function has to be exactly invariant. This group is called SL2C, and it's actually generated by 2 elements, one of which is S, which takes tau and negative tau and tau bar to roughly 1 over it, and T, which adds 1. And this group generates a group called SL2Z. And we're going to get a little mileage just out of demanding that this partition function satisfies this constraint. Moreover, the partition function can be written as a sum of characters of the theory, and the characters of the Virasoro algebra are worked out in your favorite large yellow book about 2D CFTs, and it's given by these complicated formulas that you can look up. So there's always a unique vacuum in our theory. And then I have some spectrum of operators. So that's going to be very theory dependent. And it'll depend on the degeneracies D, which will be some non-negative integers at each. A bar. And another way of writing this equation is that the name of the game is to find some function D that satisfies this equation. So when written in one frame, you get the same value as written in another frame, where this Q prime is any SL2Z image of the original Q. Now for simplicity, I'm going to assume that there are no extra conserved kernels in the theory, because if there are, then I'm already down. If there are no extra conserved kernels in the theory, the twist gap is 0. So I'm going to assume that these go over strictly, H and H bar go over strictly positive numbers, not necessarily integers, but positive numbers, and that these degeneracies are non-negative integers. And the name of the game of the modular bootstrap is to find some solution or some constraints on these degeneracies D. Actually, I'm going to tell you one interesting fact, which even at this level of a discrete spectrum with no conserved currents, and the central charge bigger than 1, I don't know of any solutions of this equation, which is quite a surprising statement. And I think if you could find one, it would be very, it would be quite interesting. So, yeah. So this equation, as I wrote right now, if I assume the central charge is bigger than 1, so I know what these forms of these characters are, and I demand that there are no currents. So these H and H bar, instead of being greater than or equal to 0, I demand it to be strictly positive. I don't know of any solutions of this equation. So you may take your favorite 2D CFT that you know, some Witten model, whatever, where you say, hey, I can calculate the partition function. It indeed is modular invariant. And you're right. It will satisfy this equation. However, there will always be some states where H is equal to 0. Now, this is probably a statement of my ignorance, or the field's ignorance rather than some deep statement, but I think it's just sort of an illustration of how little we understand like the space of these modular forms. So for example, if you ask a mathematician, this is, and you can phrase this as a math problem, and if you ask a mathematician, can you classify this? They'll freak out and say no. So you see, if you got rid of the q bars and you classified some holomorphic object, they actually know, they can give you a full classification, and it's very beautiful, and it involves these wonderful number theory functions. But once you sort of leave the promised land of holomorphicity, we know very, very little about the general space of solutions.
I think I didn't understand why that statement you're making is not already just the same as what you were saying over here. You don't know any.
Well, and I'm saying, so the statement I made earlier is on the level of the CFT. Now I'm saying a statement about the partition function. Partition function is much, much easier than the CFT, right? Just because I hand you a consistent partition function doesn't mean that the CFT exists, right? CFT has to satisfy the 4-point function crossing equation. You need to know all these CIJKs. I'm just saying, even at the level of the spectrum, I don't know the answer to this question.
Going back
yes.
to the remark about the extra conserved currents.
Yes.
Suppose we had them, and suppose
Sure.
the twist, the gap is 0.
Under Virasoro or under the parallel?
Including the extension of the
Okay,
Virasoro
great.
algebra.
Sure.
Can you offer a quick remark about what it means for what would be a three-dimensional gravitational theory in that case?
Oh, sure. So you could, for example, ask a different question for asking, which you could ask: is there a pure supergravity theory? So then, instead of the Virasoro algebra, you could look at, for example, the n=1 super Virasoro.
I have in mind higher spin currents.
Higher spin. Oh, good.
Because people like Gopal Kumar and et al.
That's
have done
right.
amazing work, right? On this.
That's true, but this is not what I would call Einstein gravity, because of course there are higher spin currents there, and some of their work is related to, for example, the symmetric product or orbifold theories.
Mhm.
I mean, I don't exactly know what comment to make. I mean, these are perfectly well-defined CFTs, and there may be some bulk interpretation. That bulk interpretation would not be an Einstein gravity. Maybe some higher spin theory, and
So the statement that T gap is 0 does not have immediate.
No. I'm really demanding a lot when I say a pure theory of gravity. For example, our world is not a pure theory of gravity, right? There are electrons, there are all of these particles. But you can ask, is there some minimalist theory of gravity we can propose where there's really nothing but the vacuum state and black holes? And so in some sense, maybe you shouldn't be so upset that there's no pure theory of atheistic gravity, because it's quite a lot to demand, and it all top-down constructions from string theory, even ignoring the higher spin ones. So don't look at orbital points, but look at the large radius point. There are always KK modes. There are string states.
Sure. Okay.
Okay. So yeah, these are very, very good questions. So let me now discuss the Lightcone limit of this in reference to this paper. So the Lightcone limit is the following limit I'm going to take. I'm going to analytically continue so that tau and tau bar are no longer complex conjugates. Rather, they're two independent complex variables. And this crossing equation, you can convince yourself, still has to be satisfied. And I'm going to take the limit beta goes to 0 with beta bar fixed, where beta and beta bar are the imaginary parts of tau and tau bar respectively. So I'm going to fix beta bar and take beta goes to 0. Why is this an interesting limit? Well, let's see what this is in the q variables. Q is e to the negative 2 pi beta, which will be roughly 1. And the t variables, q is e to the negative 2 pi over beta, which is roughly 0. So what does this mean in the cross channel? Suppose this is true. Suppose there's a twist gap in theory. This means that in the prime variables, I get all of my contribution from the vacuum state. Right? Because q prime is very small, and the vacuum state has a negative Casimir energy. So I'm rating 0 to some finite negative number, which is very, very large. And every contribution here is penalized by some factor e to the negative 2 pi over beta times h, which is a very, very small number for a positive h in a very small beta. So that means I can approximate this channel simply by this term. Yeah, you have a question?
So in terms of regular crossing, Lightcone limit meant that z or z variable was approaching the actual Lightcone of the other
That's
side.
right.
So here, is there any significance to the term Lightcone?
Absolutely. Good. So, right, as was mentioned, you can think of the usual Lightcone limit as z and z bar becoming light separated. So, good. I'm going to tell you a non-trivial fact, which is every one-loop partition function can be written as the 4-point function of a different CFT. That different CFT is the tensor product of the original CFT with itself, and there's also a modding out by some Z2, which exchanges the two operators. When you do this orbital flip construction, you introduce these twist fields. And it turns out that regular 4-point crossing of the twist 2 fields, that exactly corresponds to modular crossing equation of the original seed CFT, and the Lightcone limit of that 4-point function, which is precisely those operators in the Lorentzian signature become lightlet, precisely corresponds to this limit. It's not entirely obvious from what I said, but this is just a fact, and this is where the name Lightcone comes from. It's a good question. Okay, so what's the point? Like in most Bootstrap arguments, I'm going to take a limit where in one frame I know what the answer is. So in the Lightcone limit, assuming the twist cap is non-zero, I know the answer is just given by the vacuum, and then I'm going to take the inverse Laplace transform of this to get precisely what the expression for the density of states is. Does that make sense? So that means I get the following crossing equation. So if you sort of go through all the algebra, the crossing equation is the following. So remember, all this is valid in the limit as beta goes to 0, where beta bar is fixed. So I'll say where this equation comes from. Okay. So the left-hand side of this equation was the unprimed variables over here. So here, remember, Q and Q bar are roughly e to the negative beta and e to the negative beta bar, so I'm not penalizing any high energy states or high spin states at all. It's very small, so if high spin, there's very little penalty. Here is just the vacuum contribution. So here's the transformed into S frame, and as you can see, this is sort of the dominant term in this equation, because I'm taking beta to be very small, and this is the contribution of the vacuum. So recall for a 2D CFT, the vacuum has a Casimir energy that's roughly C over 24. So this term right here is precisely the Casimir energy in the S transform frame. So for those of you who are familiar with Lightcone Bootstrap, as is commonly the case, you have to reproduce a divergence here as beta goes to 0 with an infinite number of high spin primaries. So this is the sort of usual story, and indeed you can convince yourself that you can reproduce. And you can reproduce it, and one way you can see what you have to do to reproduce it is simply take the inverse Laplace transform of this equation. And I guess actually, good. Before I do that, I'm first going to give a very quick and rigorous argument to show that, so our goal is we're going to show that the twist gap is less than C minus 1 over 32. I'm first going to give an argument that is always less than C minus 1 over 24. This argument is due to Hartman, Collier, Lin, and Yin. And the argument is the following. Let's take this equation, and let's multiply both sides by the following. E to the 2 pi beta bar, whatever the twist gap is, minus C minus 1 over 20. So what is the beta bar dependence of both sides of this equation? Well, on the left-hand side, the beta bar dependence is very clear. It's just going to be e to the negative 2 pi beta bar, h bar minus twist gap. And by definition, h bar minus twist gap is always positive, or at least non-negative, right? Because every state has twist above the twist gap. So that means that the derivative with respect to beta bar has negative derivative. Okay? Now, let's multiply by the same factor on the right-hand side. The beta bar dependence is quite complicated. There's a 1 over square root of beta bar here, there's a 1 over beta bar here, etc. But now let's take the limit as beta bar is very large, while we first take the limit as beta is very small. So take the limit. 1 over beta is the biggest guy in town, but beta bar is bigger than 1. So we take this double order of limits. And you can convince yourself that the betas basically just come along for the ride, and all we need is beta bar is much bigger than 1. And this term here is going to be much more important than the rest of the terms of the equation. So that means that this guy better also have negative beta bar derivative, which implies that this Swiss cap is less than C minus 1 over 24. Okay. Any questions on this? So that's great. This is precisely at the BTC threshold, a leading order of the central charge.
That was quick.
I'm sorry?
That was quick. So this is your main result.
No. This is so we're going to improve this from 24 to 32.
Oh, sorry.
Yeah. No problem. So this is precisely at the BTC threshold, and we're going to push it below the BTC threshold.
Okay.
This is a very quick and slick and beautiful argument. Unfortunately, I cannot take credit for it, but I'm happy to. Okay, so now I'm going to say a little bit more about this this improved twist gap, and in particular, I'm going to show that the presence of a twist gap implies an extension of the Cardy formula. So first, for those of you who are not familiar or might have forgotten, let me remind you the regular Cardy formula. So every 2D CFT has a universal formula for the entropy of high energy density of states. So a very heavy operator is a universal form for what their entropy is. It's given by the following formula. I'll first write it out and I'll say how it's derived roughly. So roughly speaking, it's the exponential of the square root of the total charge times the conformal dimension. It's symmetric in the left and right. And the key part is this formula is only valid when h and h bar are both much bigger than the central charge. I don't need to take the central charge large, but as long as the central charge is some fixed number and I take h and h bar to be much bigger than c, there's a universal formula for the density of states. And actually it's pretty simple to derive. You simply take this crossing equation. You take both q and q bar small. That means that we know the S transform, and we do an inverse Laplace transform to get this universal density of states. Now, why did I have this condition that both h and h bar are much bigger than c? The reason is because when you do this inverse Laplace transform, you do a saddle point calculation. And you need to be able to trust the location of your saddle. Now, this calculation, approximating this right-hand side by only the vacuum state, requires that tau and tau bar are both very big, or equivalently q and q bar are both very small. So that means that the location of your saddle better be at a place where you trust your approximation, and it turns out if you kind of crank the math, that your saddle is only at a place where you trust your calculation if h and h bar are both much bigger than c. So this is the very famous and quite beautiful Cardy formula, and it's related to black hole entropy and all sorts of wonderful things. But from the way I phrased it, it hopefully is maybe a hint that we can do a little bit better than that if we assume a twist gap. Because you see, this crossing equation we wrote down over here, we didn't have to assume both beta and beta bar were very small. We only needed one of them to be small, right? So the usual Cardy formula, we take both beta and beta bar to be small, and then you always get a crossing equation. Now what we're saying is, if the twist gap is non-zero, you only need to take one of them small. Because if the twist gap is non-zero and you take one of them small, you get the whole Virasoro vacuum character. You know what that is. You looked it up in your favorite book on CXTs. So we can just run through the exact same argument as Cardy, but only take one of beta. Only take beta small. You don't need beta bar small. Beta bar can be order 1. And then, probably not surprisingly, instead of demanding that both h and h bar are much bigger than c, we'll only require that h is much bigger than c. Does the logic make sense? So, okay, I'm not going to bore you with taking the inverse Laplace transform and doing the saddle point. You can do that in Mathematica. And it turns out the answer is it's a little bit complicated, but so this is if t gap is not equal to 0, this is false. Then density of states, which I labeled by the spin and the twist. It's a little bit, but I'll just write it out. So this term, h bar plus j, is how I write h. This term is precisely the same as this term over here. But now there's a slightly more complicated formula given by the difference of two quotients. So these quotients are the same, except this is c minus 1 over 24, and this is c minus 25 over 24. So what are some sanity checks on this formula? So the first is, suppose I take this formula, and then I take the large h bar limit of this formula. It indeed reproduces this one, because what happens if you take the large h bar limit? These quotients become exponentials, and the second exponential is much smaller than the first exponential, because the argument is smaller. And then I reproduce the usual Cardy formula. For those of you who are familiar with something called the modular kernel, this is simply the product of two modular kernels. But if you're not familiar with it, it doesn't matter. I'm happy to talk afterwards. Let me just say something that's qualitatively interesting about this formula. Suppose I take the limit as h bar approaches c minus 1 over 24. So this formula is valid when h is very large. So I better take, if h bar is finite and h is large, that means the spin is very large. Right? Because j is h minus h bar. If I take this finite, that means j is very large. So I take j to be very large, but there are no j's in the quotients. So if h bar minus c minus 1 over 24 goes to 0, these quotients almost cancel. So it turns out that this formula will kind of simplify in that limit. And I'll get a universal density of states for the high spin, low twist operators. So high spin, low twist has the following form. There's an order one number, it doesn't matter. But the point I want to make is that it vanishes like the square root, and then there's an exponential factor in the spin. And then the one that's as well. Okay, so I'm going to keep this one in the box, and we'll return to it later. Okay, but sort of the summary is that by doing this Cardy-like argument, where I demand a twist gap and do this sort of Lightcone argument, I can show that there's some universal formula for the high spin, low twist density of states. Okay. Okay, any questions so far? Okay. Now, let's take a step back and ask ourselves: is this all we can possibly learn from the modular bootstrap? So is this universal density of states, this very complicated formula, all we can learn from the modular bootstrap? And the answer is going to be no. And here's one way you can see why. I think in times like this, it's really important to keep the big picture of life in mind. And we really spend a lot of time talking about the S transform. But there's a lot more to life than just the S transform. There's also the T transform. So recall that there were two generators of FSL2Z, and we've only been focusing on one of them. So let's generalize all of our discussion to the following. So far, we've been looking at this limit. Tau is I beta, tau bar is negative I beta bar, and we took beta to 0. But let's turn on a real part. Now, the S transform isn't quite the thing we want to do. So the thing we want to do is to take tau very close to the point at I infinity in the upper half plane, because at that point, then we can approximate the partition function by just the vacuum. So instead, there's another element of SL2Z, which is this element. Okay, and it turns out that this will take tau prime is equal to negative 1/2 plus I over 4 beta, and tau bar prime is equal to negative 1/2 minus I over 4 beta. So if beta is very small, then in this transform frame, which is not quite the T transform, which is not quite the S transform, I think this is like ST inverse S, tau prime will be very close to infinity, and now you can use, and now you can approximate the transform frame as just a vacuum, and again try to play the same game. So we can play exactly the same game in the board that I just erased, where we look at the transform frame, say it's given by the vacuum, and relate that to the untransformed frame, and learn something about the high spin density of states. So let me just write down the crossing equation. Fortunately, it's very, very similar to this one. If you work very hard, you'll find out that you'll get a factor of negative 1 to the j. Where does that negative 1 to the j come from? It comes from this 1/2 over here. And then some order 1 numbers change. So I think there's the 2 here.
If you took J to be, if you took tau to be something other than 1/2, say 1/4 or.
Excellent question. Yeah, so good. You can do any R over S, and there'll be some SL to Z transform. In fact, it's not difficult to do the most general case. And we do in this talk. I'm just going to focus on 1/2. But the rest of the cases are all qualitatively similar. But you're absolutely right. We can do a more general case. And in fact, this word I wrote down the most general solution. But I'll first solve the 1/2 case, and then we'll. But yes, you're absolutely right. There's nothing special about 1/2. Yeah, any other questions? This 2 becomes divided by 4. Okay, so the equation looks almost the same, but there's some very important differences. One very important difference is there's a -1 to the j. So instead of adding everything with plus signs, now half of them we put a minus sign, which would make the answer smaller. Indeed, it makes the answer way smaller. Now instead of it goes as e to the some number times 1 over beta, it goes that e to that number divided by 4 beta. So it's non-perturbatively smaller. So almost everything canceled. The odd spins almost canceled, but there's still a divergence if beta goes to 0. And now you can ask yourself, like, now there's a well-defined question. Like, I have this density of states that I wrote down here. Suppose I literally plug this density of states into this formula on the left-hand side. Will I reproduce the right-hand side? Right, as in the limit as beta goes to 0. So this is a well-defined math question. So you can, ask your well-defined mathematicians to answer this question, and the answer is no. It will not reproduce it. It will actually reproduce a term that vanishes in the limit as beta goes to 0. So let me rephrase. It'll approach a constant as beta goes to 0. So it will not have any divergence as beta goes to 0. So because this term sort of treats the even spins and the odd spins completely democratically, it turns out that there'll be a complete cancellation. Here's one way you can see this. Suppose I put this term inside this sum, and I replace the sum over j with an integral over j. Then you can do it exactly in Mathematica, and you'll find an exact cancellation. And now you can ask, what errors did I introduce by approximating the sum by an integral? And there's a whole area of math called Abel-Plana theory that you can read the Wikipedia article of and learn about the errors introduced, and you can convince yourself that the errors that you produce will approach a constant as beta goes to 0. So this term does not solve the more general modular Bootstrap crossing equation that we wrote down, which means that there's more to learn. Right? Well, it's actually not difficult to solve this equation. Suppose we're just in, yeah, go ahead.
Wait, just make sure I understand.
Yeah.
I wouldn't necessarily have expected that, right?
Yeah, you wouldn't necessarily have expected that because
Because this is only valid in a certain limit.
This is only valid in the large J limit, but that's precisely the limit that's needed to sort of get the beta goes to 0 divergence, right? Because in fact, the logic is a little bit backwards. Why is this only valid in the large J limit? This is only valid in the large J limit is because this is only valid in the beta goes to 0 limit. So when you solve this equation, you got some expression, and you can only trust that expression in a term that's important to reproduce the beta goes to 0 divergence, which is, it turns out, although it's not totally obvious for itself, is a large J limit. And well, you can actually see it's a large J limit because large J is penalized by factor beta, and if beta goes to 0, large J is barely penalized at all. Good, yeah, good question. And it's actually not totally obvious that this guy would not even reproduce a divergence because this divergence is non-perturbatively smaller than the divergence we previously encountered. So you might have thought that like, okay, almost everything will cancel, but what will survive will still be a divergence not as severe. But it turns out the answer is no. It's kind of interesting mathematical fact that the cancellation is so severe. But good. Any more questions? Okay, so let me say what the solution is. So you can actually just take this equation and let's forget about the solution we have and just say let's just try to solve this crossing equation. What rho j of h bar will reproduce this divergence? You can again just take the inverse Laplace transform and see what the answer is. So I'll call that rho j prime. I'll write it above here. So the solution for j prime that solves this is almost the same as what I wrote here. There'll just be a couple of changes. In fact, I'm not even going to rewrite it. I'll just say what the changes are. So I'm going to change the 4 to a 2. Every 4 to a 2, and I'm going to change this minus to a plus. And more importantly, I'll have a -1 to the j. So maybe I will write it here.
At the end of the day, don't you with something that satisfies all of these things?
Absolutely, absolutely. So I'm not done yet. So indeed. So first let me say roughly why this satisfies them, and then I'll address your very important point. So this term will, first of all, this term is not even manifestly positive. For odd spins it's negative, for even spins it's positive. But this term, if you just mathematically plug this in here, you can see that it roughly reproduces the right-hand side. And here's the intuition. This -1 to j will precisely cancel. So then you'll just get a sum of positive terms, and then you're basically up to some, up to some 2 pi's versus 4 pi's. You're basically reduced to your original equation. So this is some formula that will successfully reproduce the divergence to the right-hand side. But there are a number of problems with this formula. First of all, it changes sign. We have one answer that's manifestly positive. And second of all, it doesn't satisfy the original crossing equation. The way these crossing equations works is you're not allowed to have a different solution for every equation. You need one solution, and it has to satisfy every equation that you come across. So the answer is, what's a density of states that will satisfy both equations I wrote down? And actually, the answer is simply going to be the sum of these two terms. So why will that intuitively? Why will that satisfy it? This first term, it satisfied the first equation we wrote down, no problem. But it messed up with the second equation, and it roughly gave 0 on the right-hand side of the right-hand equation. It gave a constant that didn't diverge as beta goes to 0, right? And we're only, because this equation is valid, if the beta goes to 0 limit, we only care about the divergence as the beta goes to 0. So this first term, it solved the first equation, and it didn't really touch the second equation. Similarly, it'll turn out that the second term will exactly solve the second equation, but it's not going to touch the solution to the first equation. It's not totally obvious, this fact I'm telling you, but you can mathematically show it rigorously. And as someone I think asked earlier, you can ask like, well, can we just play the game with any fraction, like 1/3, 1/4, 2/3, 1/5, whatever. And you can write down some kind of complicated expression for a general infinite sum. And what will happen is there'll be a term that discriminates. So there's a -1 to the j. That means you discriminate against spins mod 2. There'll be a term for the j for 1/3 that discriminates against spins mod 3. What that'll do is it'll solve the crossing equation for 1/3 and 2/3, and it won't matter for any of the other crossing equations. So there'll be some infinite sum, and each term will solve the crossing equations with a fractional part of 1/s, will discriminate against spins mod s, and it turns out it will not matter at all for any of the other crossing equations. Okay, any questions? Yeah.
I think I'm just going to rephrase, ask pretty much the exact same question. I'm still a bit confused. It sounded like that you derived the form of your first density of states.
Right.
By solving the
Right,
condition.
right.
So, but now you're telling me that's,
Right, exactly. So good. So now you can say, wait, what went wrong? We had this derivation of density of states, and for example, it reproduced the Cardy formula. For example, like will this reproduce the Cardy formula? Like, won't this mess it up? Actually, it'll be totally fine, because imagine I take h and h bar both very big. This term, it looks roughly the same, except 4 pi got changed to 2 pi.
okay.
So now what will happen? It'll, instead of being e to the 4 pi some big number, it'll be e to the 2 pi, the same big number. That's way less important. And the Cardy formula, right, because it's e to the n versus e to the n over 2. Right. So this is a non-contributively smaller term. So generally, unless you're looking at a very weird regime, which I'll get to soon, generally if h and h bar are both big, for example, the s equals 2 term it'll be like way smaller than s equals 1 term, and in fact it'll be so smaller that like the usual arguments like Cardy, it's sort of non-contributively small, so Cardy can't even trust terms of this size.
Normally I would have thought that you just check 2 cases, right? One has to do with S and one has to do with T.
Yeah, very good.
Why are we getting 4?
Very good. So indeed, if you could exactly solve S and exactly solve T, you're completely done. And in fact, exactly solving T is not difficult. It turns out that T is exactly equivalent to all of the integers being exactly quantized. So if you could write down a spectrum with exact integers, spins, and then exactly solved S, then you're completely done. Like you can go home. But the thing is, this crossing equation didn't exactly solve S. It solves S and the limit as beta goes to 0. So what will turn out is if you take this expression and do S, okay, and then do T and then go back to S, you'll no longer have integer spins. So you didn't, so the problem is you didn't like exactly solve your equations. It's a very good question. So in principle, we could just forget st squared s and just look at s and t and like work really hard and exactly solve it. But because we're not able to do that, I think we're still able to extract interesting physics by looking at, regimes where.
Feels like you're summing over spin structures.
Going over spin structures. maybe the S equals 2 case looks like that. I'm not sure if once you go to the 3, 4, 5, etc. case, because you don't have, it's like fractional spins or something. Let me just say very quickly what the, unless there are any more questions.
Oh,
yeah, go ahead.
I'm sorry, this is
No.
just specific. I should be that. Why 4? So what happens? There are 4 pieces.
Good. Yeah, where does this 4 come from? Yeah, it comes because if you note in the Virasoro vacuum case, there's a null state at L-1 and there's a null state at L-1 bar. So if you write out the Virasoro vacuum character, there's this 1 minus Q bar term. So this is also because L-1 annihilates the vacuum. This is a very technical answer. So, and if you expand this out, there are 4 terms, and these correspond to these 4 terms. I don't think there's any particular deep reason. It's just the structure of the vacuum character.
One question.
Yeah.
Sorry. So you said the density is the sum of these two.
Right.
What if it still turns out to be negative?
Yeah, very good. Yeah, very good. So this is an excellent question. It's good foretelling. So generally it will not be negative because the first term is always positive. The first term is usually way bigger than the second term. But what if there's a regime of of twist and spin space such that the sum of the first two is negative? That's a great question. And inspired by this, let's analyze that. So let's take the same limit for this equation over here. And it turns out the cosh minus cosh turns out to become cosh plus cosh in the case for s equals 2, which means that the coches no longer cancel. So now I'm just going to add the term because now I know to add these two guys. So I'll also get a term that's plus negative 1 to the j. There's some order 1 number which I think is 8 pi squared or something. I don't remember the order. I think it's 8 pi squared times Okay, so there's a second term which is smaller than the exponential in spin, but now the h bar dependence is different. The h bar dependence goes as 1 over squared instead of squared plus. And the reason technically is because the coches didn't cancel. Now the coches got approximated by 1 or 2 or whatever. So let's take the very interesting regime of limits where I indeed take j very large, but I take the twist to satisfy the following equation. So this equation is, you take j very large, but actually in my derivation I didn't assume anything about the size of h bar other than it's bigger than c minus 1 over 24. And I can choose it so that although this term in j is larger than this term, because it's 4 pi versus 2 pi, if I make this number h bar minus c minus 1 over 24 ridiculously small, then this term can be more important, right? And I also demand that j is odd. Then I'll have a negative density of states.
So what do you make it really small?
Why did I make this very small?
No,
Yeah,
what,
because
what are you making? H bar minus?
h bar minus c minus 1 over 24.
Is it clear that you can make that as small as you want?
Yeah, that's a good question. So strictly speaking, this calculation was done in the limit as j goes to infinity, and now I'm kind of trying to cheat a little bit and change the order of limits. So I think what absolutely would not be allowed is if I took h bar very close to the vacuum, because taking h bar very close to the vacuum would no longer be in this Lightcone frame. But actually, as h bar goes to c minus 1 over 24, although the equations look special there, in terms of the original crossing equation, there was nothing really special about that value. So I think this is it's a good question, but naively it seems that there's nothing wrong with this limit, and I'll tell you more about some explicit examples here. But it is something that you could be worried about. Maybe let me say some words, and I'll say some possible examples, which will be related. So this looks like a catastrophe because, what we say is quite general, and you're never allowed negative density of states anywhere, including in this very strange regime. Actually, not only do you get negative, but you get sort of a large negative number. So if you integrate this density of states to get an actual number, you'll get roughly e to the I times root j, negative states. So very good. Now you can ask, is there any contribution we forgot in this equation? And actually the answer is yes. So here in this equation, I wrote that it's equal to this term, because this term comes from the vacuum. But actually there's another contribution, which comes from the lowest twist operator in the theory. Just like in the Cardy formula, when you derive it, you set the right-hand side equal to the contribution from the vacuum in the S frame, But there's another contribution which is coming from the lowest twist operator. So really here I should write plus, O of e to the 2 pi over beta times c minus 1 over 24 minus twist cap. Right? So whatever the smallest twist operator here, it'll also contribute a divergence to the right-hand side here. And you can say, okay, let's suppose there's some operator of twist t. That'll contribute to the right-hand side, and we can play the exact same game and say what the contribution of the density of states to an operator of twist t is. And okay, I'll just tell you what the answer is. It will contribute. I'll put it over here. It will contribute as x of with a plus sign. So the lowest twist operator will contribute this to density of states. And notice that the h bar dependence is exactly the same as this h bar dependence with this -1 integer. But it'll always contribute with a plus sign. Now, if the twist gap is too big, this has no hope of competing against this. But if the twist gap is small enough, it can compete and cancel against this. Yeah?
I got lost again because you have 4 parts over there, but here you're only adding 2 together.
No. This is just the most general form of the equation, and it turns out that this simplifies in this limit here. This 4 parts is not the 2 here. Each one of these guys originally came from 4 parts.
Oh.
I mean the exact form of it is not spoken. You could cross. Okay. So
Wait, so
yeah.
you're writing out, is this a subleading term in the original S transform channel?
Absolutely.
Okay, so it's a subleading, still divergent.
Exactly, it's a subleading divergent term.
Right.
But it has a hope of canceling this negativity because it has the same h bar dependence, the same twist dependence.
Right, so the problem up till this point is you were assuming that the only diverging term
Exactly.
was, okay.
Exactly. But there are other divergent terms coming from low twist operator. They're less important, but because we're taking this very funny limit, maybe important. And if we demand that this term is bigger than this term over here, and you do the algebra, it implies that t is less than or equal to c minus 1 over 32. So the claim is that if you don't have an operator, a twist less than or equal to c minus 1 over 32, all of your twists are above that, then these terms that we include are too small to cancel the negativity that we found when looking at the vacuum. But the existence of a single operator of twist less than or equal to c minus 1 over 32 is enough to cancel this negativity. So this is the argument that you always have to state a twist less than or equal to c minus 1 over 32. So maybe let me just summarize it just in words without any equations. If you just look at the contribution of the vacuum and you look at the crossing equations in the Lightcone limit, in order to reproduce the divergences, you'll have to have a universal form of the density of states, which has a negativity in a certain region of the spin in the twist. Now to cancel that negativity, you need to include a low twist operator that will always contribute a positive amount to the density of states. But if that twist of that low twist operator is too big, then it's not enough to cancel the negativity that you see. But if the twist is less than this value, then it is enough to cancel the negativity.
It's also, if you violate this, then you get a phase that isn't even real. Right?
I'm sorry?
If you violate this, you get a phase that isn't even real.
Why do you say that?
Aren't you getting exponential and square root? This is
No, this is 124, this is 1 over 32.
Oh, sorry. That's
Yeah.
This whole thing happening secretly now?
No. So I don't assume any. I just assume it's bigger than 1. I will comment about in the negative 2 minutes I have left. I will comment a little bit about. Let me first just say a few like two possible loopholes of this argument, because I don't want to think this is a rigorous proof. This is an argument we have, but it's not a rigorous proof. So there are 2 possible loopholes to this. The first loophole is so far we've approximated everything as a continuum, and indeed in the usual Cardy argument we approximate everything as a continuum. But for a true CFT, the spectrum of states is some discrete sum of delta functions, and in general there's an error term that happens when you approximate a discrete sum with a continuum. And there's a way of quantifying this error term, and it's a mathematical theory called Tarvarian Theory. And we don't attempt to approximate these errors because it can be a little bit delicate to try to do that. And actually, even the original Cardy argument, I think to my knowledge, the first paper that very carefully quantified the errors of these just came out in the past year. So it would be very interesting to make sure that the errors that came about from approximating this discrete density of states with a continuum are not enough to overwhelm the negativity we see. And the second loophole is that we assume a single twist state, but it's possible that there's an accumulation point at twist of low twist operators, but who violate this bound and cancel the negativity we see. I actually think that's not possible for some reasons that we can discuss afterwards, but I can't rule it out yet. So the two loopholes I would say is that we can. I'll just be honest. Is one is these Tarvarian theorems, which is discrete versus continuous, and the second is the accumulation point of the twist. And I think if people could either find a counterexample or clean these loopholes up and make this rigorous, that would be quite exciting. Although I do not know how to do it. Maybe if there's if I can go just a little over time, I just want to comment, very briefly about some implications of this result to the case of pure gravity. So as I mentioned at the beginning of the talk, so this result is nice. It's a nice universal fact. We don't assume large C. We just assume that C is bigger than 1 in Virasoro symmetry. But in the specific case of theories dual to gravity, this is quite interesting because it turns out, so I'll just say a fact. If you want to interpret states in 2D CFTs as BTZ black holes, the mass of these BTZ black hole is given by this formula. This is all in the large C limit. So if you want the black hole to satisfy cosmic censorship, so the mass is bigger than the spin, this implies L naught and L par are bigger than C over 24. And we're demanding a state less than C over 24, which again, it sometimes is not a huge shock because all of the top-down examples of ADS3 have a state way below this. But we're saying that there's no theory of pure gravity. And let me comment a little bit on what I mean by pure gravity. There are two definitions you could use when you say a theory of pure gravity, and these are two different things, and I want to distinguish them. The first definition is what I'm going to call an effective theory of pure gravity, by which I mean just some low-energy observer only sees the Virasoro just pure ADS and not pure gravitons. And the second definition is what also I call a true theory of pure quantum gravity, which means that the only states in the CFT dual can be interpreted as black holes. So let me translate that from gravity language to CFT language. I would say an effective theory of pure gravity is one where the scaling, the gap to the first non-trivial primary operator is order C. C times any number, C over 100, right? Because C is M Planck. So if the first particle you see is like M Planck over 100, any low energy effective theory would not know about it. So those theories I don't have any comment on. They may exist, they may not, and I don't have any comment on. And actually, just in case, because there's some confusion in the literature, there's a paper by Witten called 3D Gravity Revisited that some people might be familiar with, and that's actually about this case. So I have no comment about the existence of Witten's partition functions for those of you who are familiar with it. But if you're not familiar, it doesn't matter. But the second is a much stricter definition of theory of gravity, where every single non-vacuum Virasoro primary operator can be interpreted as a BTC black hole. And this is the statement that I want to claim does not exist. And there's actually a check that you can do. So there was a very beautiful paper by Maloney and Witten in 2007. I can give the archive number.
It's important that you're talking about for MC.
Well, I'm actually interested in the largest C limit. The C goes to infinity limit. Yeah. In this paper, what they do is they take the Virasoro vacuum character, and they try to sum over geometries, which it corresponds to, it turns out, sum over SL2Z images of the Virasoro vacuum character. That's a divergent sum, but they work very hard and they regulate that divergent sum and get an answer with a spectrum which satisfies that all primaries have twist greater than or equal to C minus 1 over 24. So they write down a partition function which has a spectrum violating our boundary. So it better be the case, according to us, that their spectrum is actually secretly negative. They actually found some negativity, but that negativity could be relatively easily cured. We sort of predict that if we look at this very interesting regime of high spin and low twist, that they would have a negative density of states. And we explicitly took their function and checked it, and indeed, they do have this negative. exactly where we predict. But this negativity can be cured with any twist operator below -1/32. So in some sense, like one check of our proposal is that if you take an explicit function which has a gap violating it, you can it's a non-trivial amount of work, but you can explicitly look at the spectrum in this regime and check the negativity where we predict. So just to summarize, and then I finish. We give an argument, although it's not writers, but we give an argument that any 2D CFT with center charge bigger than 1 has to have a Virasoro primary, which satisfies that the twist is less than or equal to C-1/32. And one non-trivial check of it is that this function indeed violates our bound, but also violates positivity of the partition function. So I think I'll end there. Thank you.